Hi, I'm Ben-Yaakov. This presentation is entitled Thermal Runaway as a Positive Feedback System. So what is thermal runaway? Suppose we have a system, say a DC-DC converter or some other system, which is subjected to some excitation. This could be, say, the voltage, duty cycle, current. Obviously, there is a power which is generated, and I'm talking about the power which is lossy power, which, as it dissipates in the subsystem, increases the temperature. Some of the heat is going out, but there is a temperature gradient, and the temperature of the subsystem can go up and up. And this obviously can eventually bring about some failure. Now, this is not really a runaway. In a runaway, or a thermal runaway that I'm talking about, we are talking about some positive feedback that we have. That is, we have some excitation of the system, generating power, there is loss. This loss causes temperature rise, and this in turn increases the loss, and consequently, temperature goes up, and of course, if this loop is unstable, then what you're going to see is just a runaway, and this is a runaway could be a function of the excitation, or in some system, it can build by itself due to some thermal capacity. That is, you feed in some signal, nothing happens, but as the time goes on, temperature goes up, and then you reach the point of positive feedback, and the system is unstable, of course, and then there's going to be a breakdown. So to examine this and to explain it, I'm going to use a thermistor as an example. A thermistor has a negative temperature coefficient, which means that as the temperature goes up, the resistance goes down, and this is the slope, which is negative. So if I'm exposing a thermistor to a voltage source that is a fixed voltage, then in this case, sometimes, it depends on the situation, we're going to discuss it, we're going to have an increase in temperature, and then at a given point, there'll be a runaway. So I'm going to examine this case by simulation. So first thing, we need to describe the thermistor in a way that a simulator, say a LT Spice that I'm going to use, will be able to accept, is to use a current source. And this current source now depends on the voltage across it and the resistance, which could be a function of something. In this particular case, it will be a function of temperature. This is the model of a resistor, because the resistor has a current which is voltage over the resistance, and I can make this resistance a function of, in this case, temperature. Now, in the case of a thermistor, one can show that for commercial thermistor, you can describe the resistance approximately by this equation. This is a constant. Actually, it's a resistance, and temperature is infinite. This is a constant, B, also a constant, and T is in degrees Kelvin. So this actually represents the resistance of a thermistor as a function of temperature, and I can actually put it here, and this will make this current source to behave like a thermistor with this characteristic. Now for the complete system, I have to consider the thermal effect, and I'm going to describe it by this equivalent circuit, the classical equivalent circuit, in which power is emulated by a current. The resistance, thermal resistance, is the resistance, voltage is temperature, and capacitor is thermal capacitor, and here are the dimensions of these elements. So this represents the case in which you have some power going into a system, a thermal system, which has some thermal capacitor, thermal resistance, and in this particular case, the voltage source represents the ambient temperature. So the temperature of the, say, junction or hot spot will be a function of the voltage drop on this resistor, which represents the thermal resistance. So the voltage drop is the temperature difference between the ambient and this point here, And of course, the higher the power, the higher the voltage or the temperature is going to be. So here is the LT-SPICE presentation of the basic system. I'm going to drive it at first by a ramp, a voltage ramp. Here it is. This is the voltage ramp. In this case, I've done it in a different way than I've described the equivalent circuit of a thermistor. What I'm doing here, I'm calculating the power directly as the voltage square over a voltage that represent the resistance. Okay, so this is V square over R of the thermistor. Now, this voltage, which represents the resistance, is calculated by this behavioral source through these equations that I've shown before. This is the constant, this is B, and this is Kelvin now, and I'm going to express temperature by centigrade. So this is 273 plus Celsius. So here is then power, this is power, going here. That is the voltage of this point represent the power. And now I'm sort of translating it into a current. This is the thermal equivalent circuit. Current source, this is the power. This is the thermal capacitance. This is the thermal resistance. And this is ambient temperature, which is 25. Okay? So we have a thermistor represented by this equation, calculating the power as V squared over the resistance, and this is the resistance, and then translating this power into a current source that goes into this emulating circuit for the thermal part. And here is what I'm getting. This is time, but in fact this is volts because I'm increasing the voltage as a ramp, so the voltage is proportional to time, and 1 second is 25 volts. At the beginning, the temperature is low. Notice this scale is in mega volts, which represent mega degrees centigrade. And so at the very beginning, it's very low. And then at one point, we have a breakdown, and then we have a thermal runaway, and temperature shoots up to a very high value. Of course, these are not practical physical value. This is just a simulation. And here is a zoom into what is really happening. Again, this is a swing of voltage. Start with 25 degrees centigrade. Here it is. It's going up, and here it's about 12.5. And then, as you can see here, there is a thermal runaway. Okay? So this is the phenomenon. Now, the point is that thermal runaway, as I have said, is a feedback situation, a positive feedback, as a matter of fact, on stability. So let's see where is this feedback loop here. So I'm starting with power. Okay, this is the power, which is generating a temperature, which in turn changes the resistance. And this resistance then changes the power. So here it is. This is the feedback loop here throughout the system. Obviously, it's a nonlinear feedback loop, so linear analysis is inappropriate unless you have a specific operating point and you linearize the system. And so let's have a look and see what can we do in order to sort of understand what's going on as far as the feedback system goes. So the first question is where to open the loop in order to examine the loop gain, okay, for stability and the feedback effect. I've set up this simulation circuit in such a way that we have here a very convenient point to break the loop, okay? There's no loading here, so if I break the loop, there's no current, so therefore I'm not disturbing anything. And I could, in principle, inject the signal here and go back and see what is returning. However, if I do that, then I'm opening the loop, and then I have to worry about the operating point and choose different operating points. So this is going to be very, very cumbersome. So another way to do it is explained here. Here is the system. This is the point that I want to open. And again, I don't want to leave everything in open loop. So what I can do, I can actually add here a summing junction, okay? And in this case, we have a summing junction here. A signal is going in here, going all the way up to here and ending up here. So this is the loop gain. The ratio between SF, the signal here, and the signal here is the loop gain. And then I can actually have some excitation here and see a signal here and a signal here. This could be DC, as a matter of fact. I don't have to have here any AC. I can set everything to a certain value of a voltage or sweep it, and then look at the ratio of SF, F sub F over S sub N, which is again the loop gain. And here is what I did. Conveniently, you can put here just in series a voltage source. This is a summing junction because the voltage here is the sum of this plus the excitation that you don't see, you just define it. And I defined it as a 0.1 volt, 1 kilohertz, okay? So this is the excitation. Here I have a DC. So now the loop gain is the ratio between the signal here and the signal here. And everything else is the same. So here is what happens during the time of running, as I've said. The voltage is going up, and what I see here is superimposed the S in, which I call the excitation, and SF, which is called the power sort of back. Okay? So I see them one over the other, and then I see also the temperature. This is the temperature. And of course, here they're sort of together. I can't see very much. So I'm going to zoom into 3 points. One here, and one here. This is just about the runaway. And here it is. The red is the excitation. Okay, this is the excitation. This is the returning signal. So the ratio between this and this is the loop gain. Obviously, the loop gain now is smaller than 1 because the return is much smaller than the input, and therefore the system is stable. This is the temperature, by the way. Now I moved, let me have a look here, I moved to a higher point, and as we can see, the feedback getting up. So it's becoming a larger signal toward loop gain of 1. This is now smaller than 1. And here, eventually, is just about before the runaway. I see that the loop gain is just approaching 1. And as I go up, the feedback actually is 1 plus something, some epsilon, which is enough to cause this runaway because I have a gain larger than 1. So this is a demonstration of the system as a feedback loop. Now, let's see how the system behaves when I have a large thermal capacity and I have just a constant voltage here, okay? So I'm not running here a ramp. This is a voltage, a constant. This is going to be a step function. And then what will happen is, if the power is due to the voltage and the resistance at this particular time, at the beginning, say, and then as the temperature goes up, the resistance goes down, and therefore the power goes up, and then it depends on the time constant of the system. If this capacitance is very, very large, then the temperature does not go up very fast, so it will take a longer time. But eventually, is the case of instability, then eventually there'll be a runaway. So here it is. Well, what I see here is this is again time, but the voltage is constant, okay? So at the very beginning, this is SF and SN superimposed. This is the excitation and the feedback and the feedback system. This is the ratio SF over S in, here it is. This is the ratio. And this is the temperature. Now, obviously, at this point, we have a runaway. That is, we had a constant voltage. Temperature was rising. I don't see it here because of the scale. And then at one point, the gain approached 1. And then, of course, the system became unstable. And there is a runaway here. And here is a zoom of the situation. This is the temperature. It's going up. This is the ratio, smaller than 1. Okay. And here is the two signals, the excitation and the feedback, just sort of pretty close. And as you can see that they're getting closer and closer together because, again, the gain is approaching 1. And as we approach a feedback of 1, positive feedback, then the system got into the runaway situation. So this shows how the effect could be as a function of time. That is, it starts quiet and then it sort of moves and then eventually it runs away. Now, in switch mode power system, there are some cases in which we can get runaway. I'm going to concentrate on magnetics, but in some cases you can get it in semiconductors. For example, due to the dependence of the reverse recovery of a diode, you might have a thermal runaway. But let's see some example of magnetics. Well, the first obvious situation is when you lose the inductance. Now, if I'm building a transformer, the magnetization inductance is dependent on the permeability of the material, say 3F3. And if the temperature goes up, you may reach the so-called Curie point. So the whole thing collapses. That is, you have no inductor anymore. It's like a short circuit. And obviously, for a given excitation of a voltage, say, the current will be very, very high, and eventually you'll have a breakdown. So this is one example. There is another example which is less known, and this is with the fact of aging. So this is an effect that you will not see immediately, but you may see it eventually after the system operates for some time. And V-shape is giving us some information which is not found in many data sheets. And here it is. This is the core losses as a function of time at elevated temperature. So it turns out, and this I would assume is for a constant condition, you see that if the core operates at elevated temperature, then the core losses are starting to go up. That doesn't have numbers here, just the phenomena. And I would suspect that if this is severe enough and the temperature is high and this phenomena goes on, then eventually you may hit a runaway situation. There is not much information about this, but this is something to watch. So this brings me to the end of this presentation. I hope you find it of interest and perhaps it will be useful to you in the future. Thank you very much.